Hello everyone. Today I'll be discussing the basic principles of IV fluids. At the end of this video, you will be able to describe the principles of osmosis and tonicity, be able to describe the different fluid compartments in the body, and to be able to predict the effect that specific types of IV fluids will have on the volume within different body fluid compartments. Any introduction to IV fluids needs to start with a discussion of osmosis. Formally, osmosis is the spontaneous movement of water across a semi-permeable membrane from a region of low solute concentration to one of high solute concentration, which tends to equalize the solute concentrations on either side of the membrane. That definition's a little wordy, so let me demonstrate osmosis through a brief animation. We'll start with a tank of water, and in the middle of this tank we'll place a divider, one that has pores of a very small but finite size. And we'll place this divider on wheels so it can move back and forth along the length of the tank as various forces and pressures act on it. While water appears to be a smooth, transparent, homogeneous substance on the macroscopic scale, and even on the microscopic scale, we know of course that on a sub-microscopic scale, it's actually composed of discrete molecules of H2O. This is obviously not drawn to scale. At any time, these molecules are flowing past and bouncing off each other in every direction. While some will pass left to right through the pores in the divider, an equal number will pass going right to left. Thus, the water level remains the same on both sides. And while some water molecules strike the left side of the divider, there's an equal frequency of molecules striking its right side, and thus it doesn't move. Now let's suppose we add a small but equal concentration of some other larger molecule on both sides of the divider. It could be a protein or a carbohydrate polymer, almost anything, provided that it's physically too large to fit through the pores. What happens? Well, as you might guess, nothing. If there are equal concentrations of the large molecules, provided that the tank is in thermal equilibrium, everything will seem stationary from a macroscopic perspective. Next, what happens if we add water, but just to one side? Common experience tells us that since the water molecules are small enough to fit through the pores, whatever is added to the right will immediately redistribute in equal amounts to the left and right, resulting in an increased water level on both sides. That probably seems obvious. But the interesting thing is, what if, instead of adding water to one side, we added an extra amount of that large molecule? Here we will see the process of osmosis in action. Remember that osmosis is the tendency for water to move across a semi-permeable membrane as to balance out the concentration of other molecules on either side of that membrane. Since there are more large molecules on the right, there will be a net movement of water from the left to the right, such that the concentration of large molecules on the right will decrease and on the left will increase until they are equal again. And this will cause the divider to slide to the left to make room for the newly recruited water. In essence, the extra number of large molecules added to the right will act as if they are pulling water to their side. The quantification of the attraction of water across a membrane as a result of concentration gradients of solutes is known as the osmotic pressure. Let's take a look at a slightly different manifestation of osmotic pressure. Imagine a U-shaped tube of water in which a semi-permeable membrane sits at the bottom, dividing the tube into two halves. And the semi-permeable membrane is permeable to water, but not to some physically large purple solute. If this solute is added to just one side, what you will see is water pulled through the membrane to the point that the water levels on either side are no longer even. The hydrostatic pressure necessary to counteract the process of osmosis is quantitatively equal to the osmotic pressure. In the case of the U-shaped tube, there is hydrostatic pressure at the bottom of the right side that is trying to push water through the membrane in order to even out the levels on both sides. However, it is the osmotic pressure on the right side which is sort of holding the water back from doing that. An interesting feature of osmosis is that this osmotic pressure is dependent upon the total number of solute particles per volume of solution, irrespective of the size of those particles. This density of solute is called osmolarity. The osmotic gradient is the difference in the osmolarity of the two solutions on either side of a semipermeable membrane. You may recall from high school chemistry class that there is this important distinction between osmolarity, which as above is density of solute per unit of volume of solution, and osmolality, which is density of solute per unit of mass of solvent. And your high school chem teacher made this big deal probably about why these two words are not interchangeable, and if you used the wrong word on an exam, you probably lost some points. The good news is that in physiology, the difference between osmolarity and osmolality is small enough to be essentially irrelevant. One has units of milliosmoles per liter, and the other milliosmoles per kilogram, but the numbers are virtually the same, and you should not feel too guilty about using the terms interchangeably. I'll now shift to discussing the different body fluid compartments before we apply the concept of osmosis to those compartments. The human body is approximately 60% water, of which 2/3 is located within cells, and 1/3 of which is located outside of cells. Thus, we can say that 2/3 of the total body water is located within the intracellular fluid space, and 1/3 is in the extracellular fluid space. Different references can cite very small differences in these numbers, but those differences are not clinically important. In addition, the extracellular fluid space can be further subdivided. Approximately 1/4 of it, or 1/12 of the total body water, comprises blood plasma, that is, the intravascular space. About 3/4 of the extracellular fluid, or 3/12 of the total body water, is in what is known as the interstitial fluid. The interstitial fluid is essentially everything that is neither within a cell nor within a blood vessel. It contains a variety of electrolytes, glucose, amino acids, fatty acids, hormones, and waste products from metabolism. It is essential for maintenance of the membrane potential of cells and to serve as a conduit for moving substances back and forth between cells and the blood vessels. And depending on specific location in the body, the interstitial space may also contain enormous structural proteins such as collagen, which literally helps to hold the body together. As important as these fluid compartments are the barriers separating them. The intracellular fluid and interstitial fluid are separated by the relatively impermeable cell membrane. Aside from water, most other constituents of those two spaces do not spontaneously and freely exchange. The interstitial fluid and plasma are separated by what is known as the capillary membrane, which is relatively permeable, which means that most small molecules easily flow back and forth between the interstitial and intravascular spaces. The most important molecule which does not easily go between those spaces is the intravascular protein albumin, which helps to exert osmotic pressure to keep fluid within blood vessels from being drawn into the interstitial space, which would result in lower blood pressure and significant extravascular fluid accumulation known as edema when localized or anasarca when systemic throughout the body. Before applying the concept of osmosis to these body fluid compartments, we need to introduce one more concept: tonicity. Tonicity is a measure of the effective osmotic gradient between two fluids separated by a semipermeable membrane. It's influenced only by those solutes which cannot cross the membrane. So imagine we have a single cell, and within that cell is distributed some solutes which cannot pass through the cell membrane. And we also have a glass of water, into which is mixed the same solutes at the same concentration. If we then put the cell into the glass of water, since the solute concentration is the same inside and out, there is no effective osmotic gradient across the cell membrane. Thus, there is no net movement of water, and the cell's volume remains unchanged. Therefore, we can refer to the solution as isotonic relative to the cell. What if there is a glass in which the solute concentration is less than that in the cell? After putting the cell inside, there is an osmotic gradient which favors movement of water from the extracellular space across the membrane to the intracellular space. Thus, the cell will increase in volume until the osmolarity is the same inside and out. This fluid would therefore be referred to as hypotonic. And if there is a glass in which the solute concentration is more than that in the cell, placing the cell inside it would lead to net movement of water from the intracellular space to the extracellular space, resulting in the cell decreasing in size. Predictably, this fluid would be called hypertonic. So in summary, we can refer to a fluid as isotonic, hypotonic, or hypertonic based on whether a cell placed in communication with that fluid will remain the same size, will grow, or will shrink. As just one practical example of tonicity in action in the body, consider an IV infusion of pure water. If you have any clinical experience with administration of IV fluids, you've no doubt encountered infusions of various concentrations of saline, which is another name for a solution of sodium chloride. And if you have a little more experience, you may have seen infusions of something called D5W, which is literally sugar water. But you've never seen an intravenous infusion of pure water. Why is that? Well, based on our discussion of tonicity, what would happen? Here's a schematic of skin, subcutaneous tissue, and a blood vessel. Here are some red blood cells traveling along, which start off with normal osmolarity inside and out. And here's an IV line pumping in pure water. Since the osmolarity of pure water is by definition 0, infusion of water will lead to an immediate decrease in the plasma osmolarity adjacent to the red blood cells. That is, the blood will become very hypotonic relative to the interior of the RBCs. Hypotonic fluids cause cells to increase in volume, so the RBCs will swell. Unfortunately, there is a maximum size to which all cells can grow before the structural stability of the cell membrane fails and the cells break open. Breaking apart of red blood cells is specifically called hemolysis. Hemolysis causes many problems beyond the scope of this video, but you can probably guess that it's not good. So an understanding of the tonicity of IV fluids is critical to preventing inadvertent harm. At this point, you may have already realized that tonicity and osmolarity, while similar concepts, are not the same. For one, the osmolarity of a fluid is an absolute value that can be measured in isolation, while the tonicity of a fluid is best thought of as a relative value that should be compared between one fluid and a second fluid compartment, which is usually the intracellular space. There's another important distinction. Osmolarity is dependent upon all particles of solute, while tonicity is dependent just upon those particles which exert an osmotic force, in other words, just those particles which cannot permeate through cell membranes. For example, molecules of urea create osmolarity, but they do not contribute to tonicity, since they are one of the few compounds which freely move through the cell membrane. Let's continue moving through the theoretical background of IV fluids to information that is incrementally more practical. Specifically, what is the impact of IV fluids on various fluid compartments? This diagram shows the distribution of volume among the three main fluid compartments, intracellular, interstitial, and intravascular, in a ratio of roughly 8:3:1, along with the osmolarity of each compartment. Since water moves freely between all three, the osmolarities of the compartments at any given time must be equal. Now imagine that this diagram represents the fluid status in a hypothetical patient believed to be hypotensive due to hypovolemia, and we wish to give some intravenous fluids to expand the intravascular volume by, let's say, 1,000 milliliters. What happens if we try this with isotonic saline? Remember that isotonic fluids, by definition, don't change intracellular volume, so immediately after the fluid is added to the intravascular space, it becomes equally distributed to the entire extracellular space only. And since sodium and chloride move freely between the interstitial fluid and the plasma, the distribution of volume between those two compartments is in proportion to their starting volumes. Thus, 1/4 of the infused volume remains intravascular, and 3/4 of the infused volume moves to the interstitial space. So in order to increase the intravascular volume by 1,000 milliliters, it will take about 4,000 milliliters of infused isotonic saline. And since saline is isotonic, or nearly so, as we'll see in the next IV fluids video, the osmolarity should not change. Now what happens if we take the same patient with the same initial volumes and infused hypotonic saline instead? That is, saline which has an effective osmolarity lower than that of the patient's plasma. Hypotonic fluids make cells get bigger, so therefore we would conclude that some of the infused fluids will redistribute to the intracellular space. So to reach our goal of expanding the intravascular volume by 1,000 milliliters, we will need even more than 4,000 milliliters of fluid. And notice that the overall osmolarity of the body has lowered. And finally, if we take the same patient and infuse hypertonic saline, this would cause cells to shrink, effectively pulling water out of them and into the extracellular space. So the extracellular fluid volume expands partly by the infusion of extrinsic fluids and partly by redistribution of water from the cells. So it will take even less infused volume of hypertonic saline to expand the intravascular volume. The downside to this, however, is the increase in plasma osmolarity, which among other problems can cause dysfunction of the central nervous system. So in summary, the greater the tonicity of the infused saline, that is, the greater the concentration of sodium chloride, the less fluid will need to be infused in order to expand the intravascular volume to a specific goal. However, infusion of non-isotonic fluids will affect the body's osmolarity. In addition to isotonic, hypotonic, and hypertonic saline, there's another important type of fluid that I'll discuss in more detail in the next video, but will introduce here. Any IV fluid containing osmotic pressure due to the presence of large molecules is called colloid, and the osmotic pressure due to such molecules is sometimes referred to as oncotic pressure. If a colloid fluid is infused and it contains particles of solute that are too large to move from the intravascular space to the interstitial space, what happens? In this case, the extra solute from the infused fluid will pull water from the interstitial space into the intravascular space, and thus even less volume of colloid may be needed to expand the intravascular volume. Depending on the tonicity and oncotic pressure of the colloid, it may even draw water out from the intracellular space. And here's what that might look like. We'll start off with our baseline volumes and add a small amount of colloid to the intravascular space. And you can see that only a tiny amount of infused colloid is necessary to markedly expand the intravascular volume. In this particular example, the osmolarity of the colloid is actually identical to that of the body, and so therefore there's no change in the body's osmolarity, but some colloid is hyperosmolar, some colloid is hypoosmolar, and so that won't always be the case. That's the end of this video on the basic principles of IV fluids. The next video in the IV fluids series will discuss the categories of crystalloid and colloid fluids in more detail, including specific examples of each, such as normal saline, lactated ringers, albumin, and hydroxyethyl starch.